We can also talk more about the types of ligands and classify them by how they bond to the central transition metal ion. That is, whether or not they are monodentate, bidentate, or polydentate. Mono means one, bi means two, and poly means many. When we're talking about mono or one coordinate covalent bond, bi or two coordinate covalent bonds, and poly or many coordinate covalent bonds, meaning bonds between the metal, transition metal ion, and the central metal ion, whatever you want to call it, and their attachments to those ligands. So we have a metal here, and it is with a monodentate ligand here attached to this donor atom that's a part of this ligand here. So this donor atom is attached to this metal, and then these donor atoms, part of this ligand, are attached twice to this one metal, which is why they're bident. And then this lead here, our transition metal, is attached by multiple different attachments for polydentate. And the dentate part of the name is used to describe the ligand's ability to attach to the metal ion, okay, and form those coordinate covalent bonds, okay? So sometimes people say that these are the number of teeth a ligand possesses to attach to the central metal. So instead of monodentate, you would say one tooth, meaning one particular metal donor atom bond or metal ligand bond versus two metal ligand bonds or many metal ligand bonds. So it's really going to be up to how you want to organize the information for yourself. Now, some cool facts about our bidentate ligands and polydentate ligands is that they have the ability to chelate, okay? And chelating is the ability to have all these different multiple attachments and form rings and different complex compounds at this point, okay, folks? And so, of course, with the more complex compounds, you can have a more diverse variety of these compounds themselves. Another thing is it can enhance stability as well to have all these other connections in your overall structure. A common chelating molecule is EDTA, which is used to help remove heavy metals because they're able to attach to the heavy metal and chelate the metal itself to remove it from the body, which is pretty cool. So now when we're thinking of coordination numbers, we have to think about the different types of ligands that are actually attached to the metal ion. So if they're going to be attached monodent, then yes, we only have one bond, but they're bidentate, we have to multiply the attachments of that ligand by 2. Polydentate, we multiply by the attachment that actually exists, right? So that means you will need to know a lot of the different types of ligands and what kind of attachments they make. And on your practice exam, you will see a table that's given to you. So let's go ahead and look at that table. This is the table that's going to be given to you in your exam. It's also for your practice exam. It has the molecular ion here. As you can see, it has our NH3, our water. It has chlorine, which we see a lot. It has that EDTA. It also has the ethylene diamine, which is our EN. You see a lot of common ligands. Also have the ligand names and the denticity. So denticity, is it monodentate, bidentate, polydentate, etc. It also shows you the donor atoms or the actual atoms that are making that coordinate covalent bond. And then you have the IUPAC names that you can use as well. So we're going to be using this, and you do not have to memorize this, but you will be given this table. And the goal is that you're able to recognize the charge and denticity here, monodentate or bidentate, so that you can use them to find coordination numbers in later oxidation loops. So let's do a couple of examples. As we see here, we have this Cu, Cl4, 2- complex ion, and we have this nickel, En3, 2+ complex ion. So we would have to go back to our table and identify the ligands that are attached to our transition metal. Sometimes you might even have to say, where's my transition metal? We have our nickel and our copper. Now, we have the ligand chlorine attached to our copper, and there's 4 of them. Now, we know chlorine is only monodentate. So the monodentate, that means each chlorine attachment is only going to be 4. And so because there's going to be 4 chlorine attachments around the copper, our coordination number is going to be 4. Now let's look at the nickel En3, 2+ complex. Now we know that En, or ethylene diamine, is going to be bidentate. So because it's bidentate, it's going to make 2 donor atom attachments to the central metal ion, right? So we have 2 attachments times 3 of the actual molecules. And so that means 2 times 3 is going to equal to 6. So the coordination number for this complex ion is simply going to be 6. And so now you just want to make sure that you're thinking of all the different arrangements of these complex ions that can exist simply from changing the ligand, for example. So if we were to change this to a different ligand like NH3 and there were 6 of them here, that'll change the coordination number. It'll also change the actual structure of the compound, giving it different properties as well. So the manipulation of these ligands and changing them, how they're attaching to that transition metal in the center is very cool and important way that we see a lot of these brand new coordination complexes exist. And we also can go further and say, okay, coordination number 6 means you're going to have an octahedral geometry, and this is coordination 4. We don't know if it's square planar or tetrahedral. So you'd have to have previous information or be able to answer that. So for this compound, it's actually going to be tetrahedral. Well, now that we have our complex ions and can get our coordination numbers from the secondary valence, why not also get our primary valence oxidation numbers for the same complex ions, right? So how do we do that? First, we're going to use our table that has all the information about the ligands that we need. It's going to tell us our charge, whether it's going to be anionic or neutral, and also how it is going to bond to that central metal ion and give us the coordination. Let's get into an example. How about the copper NH3 2+ complex ion we've been seeing this entire time? Okay, so first, we want to focus on the charge of the complex ion overall. You see we have our brackets, and then we have our charge, which we know from Werner is going to represent our oxidation number. This is also we can use to set equal to this entire complex. So that means we'll have this entire complex set equal to a 2+ charge when we're trying to go further and figure out exactly where our oxidation number is. So we've located our oxidation number. Next, we're going to locate our ligand. You see we have NH3. Then we're going to locate our ligand on our table. So we have NH3. As you can see, it's neutral, it has no charge, and it's monodentate. So we can say our coordination number is going to equal 6 because there's 6 and they're all monodentate. So 6 times 1 is going to equal 6. And we can also say, we can also use the neutrality or charge of this NH3 to help us solve for what we're looking for. So we're basically trying to solve for this copper here. So we're going to set copper equal to X, and then we're going to add it to our NH3 ligands, okay? So there's 6 of them. They each have a charge of 0 because they're neutral. And this entire thing, as we said before, is going to equal to the charge of the entire complex. So we have X plus 6 is equal to plus 2, meaning that we have X plus 6 times 0, which is 0, is equal to 2 plus. So therefore, our X is also equal to 2 plus. What does this mean? It means our oxidation number for our copper is equal to 2 plus, okay? So that's how we'll go about getting the oxidation numbers. You simply have to make sure you're consolidating what the charge of the actual complex ion is, figure out what the charge on the ligand is, and then solve for your transition metal. You want to get used to being able to read the complex ions and gather information about them. So right now we can say, okay, coordination number 6, this is all extra information. We can also say it's octahedral geometry. And even though it's extra information, it's just going to help keep our minds and our brains primed as we keep going along and layering material. Okay?